In this lesson, we have yet to see feathers with an asymmetrical form, but that time has come. To make the functional jump from displaying to flying, theropod feathers had to evolve an asymmetrical form. The asymmetry of true flight feathers is essential for the wings to generate lift and thrust. Without that form, birds cannot fly. This brings us to the topic of feather development. It was once hypothesized that feathers evolved directly from large plate-like scales. The concept was this: to become feathers, scales became raised up at one end and stayed embedded in the skin at the other. So the thinking was that the broad, flat form of most modern bird feathers had been present right from the start. As it turns out, that's not the way it happened. Developmental studies of modern bird feathers have charted how feathers grow into their complex forms. Combined with the new fossil record of feathers, it's now possible to piece together the various stages of feather evolution. In stage 1, feathers began not as flat scales, but as projecting filaments with simple, unbranched, cylindrical, and hollow forms. Stage 1 feathers account for the hair-like body coverings of most non-avian theropods. In stage 2, the hollow cylinder splits into multiple small filaments called barbs. And barbs radiate as a tuft from a single base. Some stage 2 feathers are present on dinosaurs like Sinosauropteryx. The third stage is usually broken down into two important sequential components. In stage 3A, a central rachis develops, from which all the barbs radiate at various points along its length. In stage 3B, the barbs develop additional filamentous branches called barbioles. In stage 4, the barbioles develop a hooked form that allows them to grip together with the barbioles of adjacent barbs, like Velcro. This is what can turn a feather from a filamentous branching structure into a unified, continuous shape. We call such feathers pinnaceous. To better convey how the hooking barbioles work, let me show you a simple demonstration. If I tug on a section of this feather, I can unhook the barbioles and effectively unzip the feather. But the connections can be zipped back up by pressing the split portions together, starting near the rachis and progressing outwards. Ta-da! The ability of feathers to zip and unzip makes them durable because they can give way under pressure and then be quickly repaired by a simple preen of the bird's beak. This feather also illustrates the fifth and final feather development stage. In stage 5, the barbioles on one side of the rachis are reduced in length by comparison to those on the other side. This is what is meant by an asymmetrical flight feather. The asymmetry is what allows feathers to serve individually and collectively as airfoils and also helps to control air flow through the wings. Thus, an asymmetrical feather is not common on the bodies of even modern birds, but are generally regulated to the wings and tail. So far, we have only discussed non-avian theropods with feathers representing stages 1 through 4. To achieve stage 5 would likely require the need for airfoils and the evolution of flight. And that requires us to return to John Ostrom and Deinonychus. Let's test your linguistic knowledge of Greek roots. What does the name Deinonychus mean? Here's a hint. You've encountered the Greek root dino before. Does Deinonychus mean A, terrible claw, B, winged beast, C, deadly thief, or D, stiff-tailed lizard? The correct answer is A. Just as the name dinosaur means terrible lizard, translated from ancient Greek, the name Deinonychus means terrible claw. Deinonychus has a striking feature, an enlarged and sickle-shaped claw on digit 2 of the foot. This is not the foot of Deinonychus, but its more famous Asian relative, Velociraptor. Deinonychus and Velociraptor belong to a group of theropods called the Dromaeosauridae. Dromaeosaurids form a clade with two other major theropod groups, the Troodontidae and birds. We call this group the Eumannaraptora. It's important for you to be aware that the exact relationships between the three groups that comprise it are unclear and currently the subject of intensive research. Eumannaraptorans have long arms, long fingers, and enlarged sternum. They also have tails with a reduced number of vertebrae and greatly reduced musculature. In most other dinosaurs, the base and front half of the tail supported a large muscle set that powered retraction of the femur in the leg. The reduction of this muscle in Eumannaraptorans fundamentally changed hind limb locomotion, bringing it closer to the high knee-bending style of modern birds. The tail reduction also moved the center of body mass forwards to in front of the hips. The Dromaeosauridae and the Troodontidae are placed together in the single group, the Deinonychosauria, because both share the enlarged foot claw. Take a closer look, and you'll see that the tubercle for the attachment of the claw contracting tendon is positioned low. You will recall from lesson 2 that such a tubercle position is generally indicative of high speed action. Also, the claw is relatively compressed with a thin inner surface to the curve. Unlike the carnosaur hand claws that we examined earlier, this claw seems equipped for stabbing and then slicing. There have been a number of interpretations of Deinonychosaur claw function. However, the leading explanation is the same one that John Ostrom proposed in his original description. He suspected that the claw was used as a slashing weapon. He envisioned Deinonychus as attacking its victims with powerful and lethal kicks. To support this idea, he noticed that the toe that bore the claw could be carried in a raised position, with the claw up and off the ground. Indeed, the claw is often found in this retracted position in fossil skeletons. This meant that the claw was held up when the Deinonychus was walking or running, and this would prevent the claw from becoming dulled and would keep it lethally sharp. The same adaptation is found in the slashing claws of modern cats. Cat claws are most often held up in a retracted position. In addition, Ostrom noted that similarly enlarged claws are present in some modern ground birds. The giant flightless bird, the cassowary, is known to use its enlarged foot claw as a kicking weapon when threatened. In addition, the South American Surima uses its claw to butcher prey. Deinonychus also raised the bar for dinosaur intelligence. But how could paleontologists assess the dinosaur's intelligence? Was it by A, determining if the dinosaur could solve simple arithmetic, B, identifying an opposable thumb, or C, measuring the relative size of the brain case? Paleontologists can roughly estimate a dinosaur's intelligence by comparing the size of its brain case against its absolute body size. So C is the correct answer. The troodontid Deinonychosaurs have the distinction of being among the smartest of known non-avian dinosaurs and of being the personal favorites of Dr. Philip J. Curry. Here he is to talk about troodontids.
To me, one of the most fascinating dinosaurs is Troodon. Now, Troodon is a very ancient dinosaur in the sense that it's 65 million years old. but it's also very ancient in the sense that it was one of the first dinosaurs ever described. The teeth of Troodon are so distinctive that when a tooth was found in 1854, it gave a name to a dinosaur. We did not know what that tooth belonged to. We did not know that the dinosaur looked like this at that time. In fact, it was more than a century later before we found the teeth in the jaws and figured out exactly what Troodon looked like. There was a lot of argument, in fact, whether this was a tooth from a lizard, a carnivorous dinosaur, or possibly even a herbivorous dinosaur, which sometimes have teeth at the front of the jaws that look like carnivore teeth. The teeth are very distinctive in the sense that when you look at those teeth, what you see is they're small. There are many of the teeth in the jaws, but those teeth, in fact, have very large serrations. The serrations on the teeth of Troodon are as big as the serrations on the teeth of a Tyrannosaurus rex. There are a lot of things about Troodon that are interesting beyond its teeth and its history. When we look at the brain size, for example, we see that the brain in Troodon is relatively large. And we can estimate the brain size by looking at the inside of this region of the skull, which is, of course, a hole that the brain filled. And these brain endocasts are so well preserved, you can not only see the overall size of the brain, but we can also see different parts of the brain itself and all the nerves and blood vessels associated with it. The cool thing is that although the brain is very conservative in a lot of ways in Troodon, nevertheless, we can see that it's a lot bigger than what we would expect to find in a reptile of this size. So if we compare Troodon brains to the brains of a crocodile, which are about the same body weight or length as is Troodon, then we see that Troodon has a brain that's 6 times bigger than the brain of an equivalent size crocodile. That tells us that this dinosaur, in fact, had a brain that's about the same size as what we find in some modern birds or mammals. And when we look at the birds and mammals that live with this dinosaur also had a brain that was bigger than most of the birds and mammals that lived at the same time as this dinosaur. The animal is also fascinating for many other reasons. When we look at the eyes, for example, the eyes are very, very large. More importantly, though, when you look at the animal from the front, we see that the eyes are facing forward to a certain extent. That means it has overlapping fields of vision, and that allows this animal to see in 3 dimensions, the same way that we do. There are characters associated with the ears of this dinosaur that suggest, like some modern birds, it was able to distinguish what direction sounds came from. When we look at the hands, we can see that the hands are in fact specialized for grasping in a certain way. And this dinosaur was also a very fast dinosaur. And we know that from looking at the hind legs. They're long, they have elongate lower parts of the legs, and this allows this animal to move very rapidly and, of course, to escape predators that lived at the same time as it and were larger than it. Finally, when we do the comparison to other types of carnivorous dinosaurs, we can see that troodontids are, in fact, very closely related to the dromaeosaurs. They, in fact, have the same kind of raptorial claw on the hind foot. But there are other differences, and they show these animals were going in a different direction. So, for example, they have long, flexible tails. And those long, flexible tails and many other characters in the skeleton suggest that Troodon and its relatives may, in fact, be closer to the origin of birds than the dromaeosaurs.
In addition to having an exceptionally large brain relative to its body size, Troodon also has a set of large eyes. This tells us something interesting about its behavior. Which of the following modern animals also have exceptionally large eyes compared to their body size? More than one answer may be correct, so check all the answers you think are correct. A, owl. B, flying squirrel. C, tree frog. And or D, rhinoceros. A, B, and C are all correct. What do these animals have in common? They're all nocturnal and need good vision. The large eye sockets of Troodon suggest that it too was often active at night.